And let's move this over here. Hello, I'm just setting up. I want to watch the. Um, I want to watch the stream in YouTube Studio as I'm talking, just in case it is going wrong or something. There we go. Yep. So now I can see it. It says I have an excellent connection. That's good. Okay, so let's start with this one here. It didn't call this a half-wave rectifier, which I find is odd. It called it a diode limiter. So I would say, like, we're going up and down at 40 hertz here. So at 1 voltage, this is gonna, well, I think it's gonna just drop it down by 0.7. Let's just find out here. Yeah. So you see here, we'll just slow down the simulation speed a little bit. By the way, you probably, if you've watched these before, you may notice that I'm trying out the let's see. I'm trying to do a vertical one. I don't know if it's actually doing it, though. It looks like it might still be just be doing the full size stream. But I was wanting to do a vertical. Anyway, so what it's doing, this is outputting what? Yeah, so 5 volts. So right here, you see we're not going to get moving until we get above that 0.7 volts, which is diode drop. And at that point, oh, I see. So it's only going to really get to 0.7 volts, that diode drop there. The rest is going to be burnt up along this resistor. I see, that makes sense. That's why it's called a diode limiter. It's sort of like what I was thinking they might be talking about, which was a diode clamp. I should have actually seen that before. Zener diodes. Let's look at the voltage reference. I just want to do some diode stuff because, like, you know, I should know it pretty easily. But, well, I might not, and then that's why I wanted to look at it first. And the reason why, like, I was thinking I should do that is that I generally like it when people can explain simpler stuff to them, to other people, just because then that shows that you truly do understand it. But anyway, so we're going again. AC source. Oops. Yeah. Let's just go. No, can't go that far down. Okay. It looks like we're going from. Up here, let's go. V 1.98. I just want to see. Can I edit there? Okay, max voltage, DC offset, 6.7 volts. Okay, so it's going from, I guess, 5.7 volts to 7.7 volts is how I would understand that. And then this Zener diode here, default Zener, cancel. So it must be set at 5.5 volts. Because what a Zener diode would do... That's an odd comment. Oh, I can put the user on timeout. Yeah. Sorry, somebody had just made uh, not a nice comment, so I used a thing. I guess you can put a user on timeout, which I didn't know of that, but now I do. Anyways, so what a Zener diode will do is it will conduct in the opposite way. So most diodes won't conduct this way, right? They will block the current that way. But a Zener diode will conduct current this way, and then the voltage will be held right at that point. So this one will basically hold the voltage right here at this 10K at 5.5 volts. Let's just see if that is correct. And yeah, we're basically going from 5.4 volts to 5.5 volts. There's somebody just asked what this is. It is just a stream where I talk about circuits, basically. If you're wondering, that's what I do on this stream, is I just talk about circuits. As I was looking, I have before, I one time I made this stream, I marked it as a what's it called, a gaming stream, which it isn't. That's I double checked to make sure I did mark this as a education. Anyways, let's go. And this time I'm doing, yeah, thank you. I think it's interesting too. This time I'm doing some circuits that I really should know very well, because I've dealt with them before. But I just want to, make sure that I do know them well, that I'm not, fooling myself sometimes. Let's just stop this one. Because, sometimes you can get overconfident, and that's never good. So, this is, as they said, it sort of gives it away when we look at the name of it, but it's a half-wave circuit, or half-wave rectifier. And why it is a half-wave rectifier is that this is obviously an AC source, which is 40 hertz. I don't know where in the world it uses 40 hertz, so I don't know why they chose that. But anyways, it's they chose 40 hertz, and it's going from, yeah, it looks like it's going from 5 volts. Yeah, max voltage 5 volts. So it's oscillating between 5 volts and minus 5 volts every 1/40th of a second, I guess. So what will happen is that when this sees a positive voltage here, this will let current flow through, but we're going to experience a 1 diode drop, which is roughly 0.6, 0.7 volts, And so since we're going from there 5 volts up to 5 volts, that means that we'll see 4.4 volts to, 0 to 4.4 volts, because if we see a voltage here, well, then this is actually going to block everything. So then we won't see anything here. Let's just see if that happens. Let's slow down the simulation speed. I like slowing it down just to, I think that I can see it better. So we're getting 4.4 volts, and then it's stops for a whole section of it. And you see, now we're into positives again. It's going to start conducting. Then we top out at, well, that was, yeah, about 4.4 volts, which is 5 volts minus that diode drop. So, what we thought. Let's go to a full bridge rectifier. Just watch in the chat in case anybody has something to say. Okay, let's stop here. So this is a full bridge rectifier or full wave rectifier. Now this is very similar to the first, like that half wave rectifier that we were talking about. But this one, so let's go through the thought experiment again. We have plus 5 volts here. Well, we're going to go through here. We're going to be blocked here. But we'll go through here. And then out. And through. And then this load will go through this way. So what we're going to experience is the current's going to flow this way. There. Into the load. So we're going to have about that 4.4 volts again here. And then out, down, and into the ground, or back into where the AC source is. Let me see if that's right. So, but yeah, no, we'll have a diode drop here, then another diode drop here. So actually, we're going to lose about 1.2 volts there. So this is only going to be like 3.8 volts, maybe 4 volts. Now let's say if we have a minus 5 volts here. Well, then we're actually going to conduct through this way, then through the load, and then back out this way. Yeah. So then, yeah, I know I did that right. Yeah. So then we'll have about the same that I was talking about before. About up to 4 volts. So let's just run it and see if that's what we see. Let's slow down the simulation speed again. I'd just like to. So yeah, we see it's going through. Now it's going this way. Ah, yes. So that's what I was doing wrong. So you see, I explained that wrong there again. So what I should have done is said, think about it from right here. When we have the minus, when I said, okay, we have minus 5 volts here, I should have said, no. We have plus 5 volts here. So when we have plus 5 volts here, we're going to travel through this diode into the load, out this way. And yeah, so see, that's why I like doing these lists. Then it gives me a chance to talk about the circuits myself, which I always find is fun. Does anybody have any questions or comments, concerns? No? Well, we can move to the next one. Do another. Oh yeah, let's just add a filter. So now what happens is with these rectifiers is that you had that, like, remember in the last circuit you always had that that drop down. So it would go up, then down, and then it would hit 0, and then it go back up and back and forth, back and forth. So what you can do is obviously you can use a capacitor. So the capacitor, so let's say we have 5 volts here again. Now that means we're going to be applying 5 volts to this capacitor. So it's going to charge up. And then we're going to go through there and out again like we were before. Now we're going to go close to 0 volts. Well, this capacitor has charged up to 5 volts. So now it's going to start discharging through this resistor. So that means that we're not going to fall all the way down to that 0 volts. Let's just see. And yeah, you see that's what we're seeing here. It's charging up. Right there. Yeah. That's a very interesting one. No, I think now I am going to go to one of my textbooks again. And we'll do some circuits from there. I'm going to do the Microelectronic Circuit and Devices by Mark Hortenstein this time. And yeah, we'll just see how it goes. So page 50 is where I'm going to start off at. It's going back to the op-amps. Page 50 and 51. Okay. And it's just a difference amplifier. So I will delete this out. It's actually quite pertinent because I made a difference amplifier for myself. Distorted it from what's it called? PCBWay to just turn a light, an LED on and off when I wanted to. Inputs and sources. We'll just do a 1-terminal voltage source. My dog's sniffing something. I'm not sure what she's doing there. There. Move that 5-volt one there. Put this one here. Then draw, add wire. There. Oh, I better stop this, or else I won't know. I need to analyze the circuit before I have it running. That's what I usually try to do. If you hear some squeaking in the background, that's my dog. Obviously not me. I don't know if you would think it was me. I don't tend to squeak things that much. At test point. Just add a test point to the output here. And then I will say view in new scope. There we go. So now we got a test point. 0 volts. Let's see. We got 5 volts applied here. So this is going to, yeah. So these two, as our op-amp golden rule say, it will always want these two to be the same. So this is going to attempt to make this 5 volts right here. So that means that we are applying 5 volts here. I think we need to move this there. Let's go 2 volts. Okay. Just think of this for a bit. If this is 5 volts and this is applying 2 volts, that would mean we would want we would want this to output some negative voltage that would compensate for this having plus 2 volts here. Just trying to figure out how much would be. Well, yeah, here, that's the easiest way. So we know we would want to have 5 volts here. So that means that we must have dropped we must have gained 3 volts there. That means there must be some current moving this way, right? No. Okay, so we got 5 volts here. Yeah, so current must be moving this way. So we got about 3 milliamps moving this way. Then it's gonna try. Oh yeah, I guess because this is the non-inverting input, so that's the one that we would be gauging off of. This is negative feedback, but yeah, because this one, yeah, so it's gonna try and raise it up. So that means we have 3 milliamps going through here. So I would say we would have about 11 volts here. Oh, no, wrong. 8 volts. Let's see. Yeah, so we do have 3 milliamps going through here. Oh, yeah. No, that's right. Because this one only has, yeah, no, that makes sense. Because, yeah, the 3 milliamps times 1K equals 3 volts. So, yeah, that's what would happen. Okay. I think we can move to the next one. Unless anybody has any questions, comments, or concerns. No? Keep that there. Now it wants us to add an attenuation network, they called it here. Which is basically some resistors. Draw a... I should do some logic ones later, because that's what I was doing just recently, and I actually bought myself an icebreaker. An icebreaker is a logic gate or programmable logic controller. No, that's not really what it is. An FPGA is what it is, a field programmable gate array. I wanted to get a like a simpler one, like a complex programmable device, but I couldn't really find one. Anyways, we know that only, like, no current, since this is a perfect op amp, not real op amps won't show this, but this is perfect op amp. We know that no current's gonna flow in to the input. So that means that we're going to have 2.5 volts here, basically. So we still have 2 volts here. That means this will want 2.5 volts. That means half a volt is burnt across here. So that means that half a milliamp is going to be going through. So that's half a volt here. So that means that this will be outputting 3 volts. Right? Let's see. Okay, good. We are correct. Now let's go say this is 5 volts. Apply. Okay. So this is 5 volts now. We're still going to want to see 2.5 volts here. Sorry if you can hear my heater in the background, but it's not too much I can do about that. So yeah, we got 2.5 volts here. So that means we'll have 2.5 volts here. So that means 2.5 volts must have been burnt across here going this way. So that means 2.5 milliamps is going. So that means we're going to have 0. Yeah, 0 volts. 2.5 milliamps speed socket. Stop. Say this is going to be 8. So now, obviously, we'll still have the same, like 2.5 volts. That means we will have 5.5 volts across here, right? Yeah. So that means 5.5 milliamps. That means we're going to have minus 5.5 volts. Huh? 5.5 milliamps. Oh, yeah. No, I forgot there's 2.5 volts here. So that means 2.5 volts. And we just need to make up the difference. So 5.5 or minus 3 volts. Yeah, no, that makes sense. Okay. I think we'll move on to the next circuit, which I picked out, which is on figure 2.17 on page 56. Is a summation amplifier. Okay. Oops. Wrong. Oh. There we go. So now a summation amplifier we would do add active building blocks. This one has the minus on top. I actually forget exactly what a summation amplifier does, so hopefully I can analyze it here. Otherwise, we'll just simulate it. But either way, we will have fun, right? Oh, yes. So that puts a bunch of resistors. We're in an extreme cold warning here in Saskatchewan, I don't know. You know, so I'm still shocked at how much my dog will go outside. He's inside now. He still has been going outside quite a lot. Right now, I think she's trying to get my attention by putting a toy. She brings her toy up to me and like puts it along my back. Now she's just sort of hacked there a bit. Why? You know. Let's go draw. We need to add the feedback resistor. Probably keep that one at 1K, but we're gonna have to figure out just gonna throw the toy for her quickly there. We're gonna have to figure out what we would want to use for these. Oh, oops, no, that's not. And draw. Put some sources. I want to add a test point. What I want to do. Outputs and labels. That's where it is at. test point. Right there. Right here. Good. So now we got that test point there. Let's keep drawing in all the wires here. See, all of these just sort of go all together. But yeah, just comment or like, whatever. Let me know how you like this stream. I'm trying something different. I decided to try to make it into the phone one, so like the vertical format this time. That was mostly because I've noticed when I do that with my phone, what was I looking for here? That I do that with my phone for my soldering videos, and I notice that I get a lot of people just showing up, and I figure it is because people are swiping and that, and I don't know if you thought that this is an annoyance to find in your swiping, and it's like, oh, I don't want to see somebody talking about circuits, or that's too much like school. Then I don't know, you can comment that, or if you like, oh, this is a nice break from. I always find that it's like sort of sad people talking. I don't know if you find that. So I just thought maybe this would be good. Some people might like it. Anyways, I think we got this circuit ready. The beer I'm having today, when I poured it into my cup, it had a bunch of chunks come out with it. Which, I'm not going to say who made it, because I do not mind their beer, but and I think it might have been that it got a little bit frozen in my fridge. But still, it's a little bit odd watching chunks in your beer, eh? Have you ever had that? Not the best thing. Anyways, so I'm going to apply 5 volts at each of these. We're applying it to the inverted input. So that means we're going to see a negative output here at the test point. I already know that by looking at the circuit. Didn't have to do too much thinking for that one. But I think we're going to have to do some more thinking now. So this one is going to show 2.5 volts there. And this one is going to show, well, that's an odd one. I put in some weird values here. Let's go here. Oh, that was 5.6 ohms. No, we want 5K. Okay. And we'll do 10K here. Sorry. 10K. Okay. So that means here we will have 1/10 basically, so a half a volt. And there we'll say we'll have a volt. It's 1.5 volts. There we're going to have, let's say, 2 volts, 3.5 volts, and then there we get the 2.5 volts, so that means we're gonna have 6 volts. Let's just see. Not 9 volts. Microvolts. 90 microvolts. Just having a think here. I see. I should have been thinking of currents, not the voltage per se. So, let's go back to what I was saying before. Let's just pretend that I wasn't talking about volts like a bit of a nincompoop. So here we're going to have half a milliamp going through. Right? Yeah, half a milliamp. This is going to be half a milliamp here. Contributed 1 milliamps, so now we're at 1.5 milliamps. This will have 2.5 milliamps, so that is 4 milliamps. And then this will have 5 milliamps, so that's 9 milliamps total, right? Yeah. So that means we're going to have that coming through here. So that means that it will have minus 9 volts to compensate for that. 9 milliamps flowing through the 1K resistor. Yeah, so that's pretty cool. The reason it is called a Summation amplifier is, well, it sums all those currents. I thought it had something more to do with voltages. But yeah, it is summing all those currents, so I'm going to just go with that. That's why it's called a Summation amplifier. Is that like it's summoned, so like we got the 5 milliamps here, and 2.5 milliamps here, 7.5 milliamps, and then 1 milliamp, 8.5 milliamps, there. That's all summed up. So you add them all together, and you get the 9 volts. Well, you get the 9 milliamps, which is transmitted into the 9 volts right there. Yeah. Let's stop this one. So now, the last circuit I was going to do for the day, I think we might do a nice, easier one first. So the last circuit I was going to do for the day is a fairly... Oh, no, we only have about 15 minutes left. So, then I'm going to go upstairs to bed, basically, because I'm boring. It is a more difficult circuit that I'm sure I'm going to bungle talking about it. But the reason I want to talk about it is that I am planning to update my dusk to dawn circuit using something similar to this. So, the reason for that is because this is a MOSFET differential amplifier. And my thought process is, I think that it might be a little bit flawed, but my thought process is that a MOSFET differential amplifier, because MOSFETs have very little current going into their gate, like the gate voltage has little to no current moving through. Ah, 514. I can't read my own writing. That's why I had a very confused look on my face. It's because I couldn't figure out where it was. So we're going to look at figure 8.27 on page 514 of microelectronic circuit and devices, which is a MOSFET differential amplifier with MOSFET loads and a MOSFET current mirror. Yeah. Then I might look at this later after I bungle this explanation, because I think what did I hit? There we go. Yeah, we will just try this out quickly. these are all N MOSFET. Okay, draw. Active components. Yeah, and this is if anybody is really interested in electronics and that. What in the hell? They could help me with the understanding of this circuit. There we go. Okay, wrong way. Draw. And sources. No, this one. Active components. MOSFET. One second, I just think I should read this first. You know what? I think I might just do this circuit later. Might do it at the start of a session so that I have it all drawn out and I'm ready. Yeah. But let's go back and we'll try and talk about some MOSFETs anyways here. Common source amplifier. Here, yeah, sure. So. No. Here, yeah. 2-to-1 mux. Ooh. Counters there. Let's do a counter. That's a flip-flop. Ooh, a JK flip-flop. In the book I'm reading, they say that I almost would never encounter these anymore. But anyways, let's look. So that's a decimal display. Okay. So this is what will be the counter. What is that like that? So when we clock it, what's going to happen here, that will flip this to either a 0 or a 1. And then when that goes to 1, this will sort of clock this one, which will sort of just rise down the line. Let's go there. See? Here, you know what I like to do? But yeah. Let's just slow down the simulation speed. So this one here, that's a 0, that's the 1. Okay, now it's 1 there. So now we're gonna hit. Okay, now we went to 0, so now that hits down to 0. That trails down all the way through here. Now we went back to 1. Goes all the way there. Yeah. I just went and I just got done these. I think I do need to do them more again. Especially since what I think I want to do once I get my my icebreaker, which is that FPGA I was talking about. What I want to do before it is that I want to actually make a few digital circuits that are more complex than what I would experience or that I have done before, so that I can sort of do those first, which has to do with these. Right now I'm just sort of, honestly, I'm just showing some different ones. Ooh, what's a spark gap there? Sawtooth generator. Here, no, wait. Spark gap. Let's fill this down. I don't know what's happening here. I see it's charging up the capacitor fairly quickly. And then eventually I bet that's just gonna spark between it. Let's see at the very top there, I bet. Let's just watch it. There. Now it's done. That's pretty cool. 2 kilovolts. Holy. Very much. Look at the internals. This is a 555 generator. I think I might just circle through some of these until I'm till it's 9, and then I'm done for the night. Oh yeah. Yes, it is a free software. It's actually just, it's not even a software. If you look, I don't know, can you see at the very top of the screen? I'm actually just in a browser. And that's really just a website. It's a very awesome, I think it's, here. I'll just say yes. Yes, it is. It is actually just a free website. Yeah. Here, since we are, so maybe I'm guessing this is a guy, Paul Falstad. Yeah, there's just a bunch of applets. Some education applets I wrote to help visualize various. By I, that's this guy, not me. I haven't actually made this. I didn't make this at all. This is somebody else who, like, it's an awesome thing. I use it all the time. I would encourage. I would say that it is better to do breadboard circuits, but I do tend to. I use this a lot because it's just people like to show it live like this. It's much easier. Yeah. This is the internals of a 555 timer. It's very cool. Let's go. Oh, here's a good one. Sample and hold. Stop. So this is a sample and hold application using a gate, a logic input. Okay. What is going on here, actually? Oh, I see. Okay, so this is the AC source. So now you see what I did there. So this is the AC source here, and it's moving there, whatever. And now, if we wanted to sample it, we have, so this will trigger the current, or like the voltage, to flow through this switch, this gate switch here, which will cause this capacitor to charge, which will hit this one, and then that will require this to output the same as this to match this input, or to match these inputs here. But it's gonna hold because once this capacitor charges, it really has no way to discharge. So let's just do Do it again. So there. So now you see we have changed. Again. So every time we do it, we will change some. Right at 5 volts here. 3.11 volts. That's pretty cool. Yeah. I want to see if I can get to a negative one. There. Oh no, I just got it close to 0. Anyways, I think we got what that one does. Am I an electrical engineer? Not really, no. I was a applied physics major in university, and now I work as a production engineer at a manufacturing company, but for the last, like, I don't know, say 6 months or so, I've been reading a lot, or I've been doing a lot of the I've been reading through the Learning the Art of Electronics book, so that I can get better at designing electrical devices, which I had been doing in my free time a lot, and just wanted to get to be doing them more, because I think that there's a lot of potential to make data collection devices for use around the farm, which I actually farm myself at here in Saskatchewan. And so, just to give some background, because I'm thinking I'm gonna end the stream soon, but I was having a lot of trouble. I was running into a lot of roadblocks. Um, when I was trying to design my own devices, because there was a lot of things I just didn't understand, and there was a lot of things that I didn't think of. Whereas now that I've went through this book a lot, as you can still see, I obviously don't have a great grasp on everything, but now I have sort of been acquainted with basically anything that not anything yet. I'm only halfway through but well, I'm not halfway through the book. 750 pages out of 1100. Oh, Ontario, that's cool. Yeah. So then you'll probably be watching the Four Nations too. Here, I'm gonna switch to another circuit. But I'm planning to. Oh, you know what we could look at? Yeah, that will be the last one here. So let's stop there. Yeah. So yeah, in basics, I'll just yeah. Yeah, so basically, I'm not an electrical engineer, but I aspire to be, or I try to do some electrical engineering stuff in my free time, and I'm trying to do it sort of as a profession as well, but not quite there yet. Yeah. So let's look at this as the last one. So, yeah. But yes, thank you. Is the Rohit is how you would pronounce your name? Yeah. Thank you for talking here. I'll go give a thing there. Wow. But yeah, thank you for commenting lots here. It's great. I love interaction. So this is an OR gate. It's also an OR gate. Oh, thank you. Yes, I think I'll like it too. I was talking to people about whether or not I should learn to do it. Oh, thank you. That's good. I'm glad I pronounced it right. I always get nervous. But yeah, I was asking people about if I could learn, and because like for a lot of the applications I want to do, I won't necessarily need that capability. But again, like the point that I was trying to do when I started going through this whole book was to get acquainted with basically anything that I could need, so that I would be aware of what I can do, or what I could use. Anyways, let's look at this. So this is basically a traffic light circuit, and they're using a 555 timer to clock right here. So it's going to go from this one. Oh, nice. Electromechanical engineering tech. And what college are you going to, if I may ask? Yes, we'll just be cycling through this basically. Okay, and then when it hits here, so yeah, it's gonna cycle through here, and then eventually we'll hit this one. Umber. I'll have to look that one up. I don't know if I've heard of that one before. Yeah, if we have this one here, this is also an OR gate, so then this will both be the same. So that means that this will be off. So that means that this red light will be off. And right there. We won't have either there. Let's just run this. Oh, this is green. Sorry, I'm red-green colorblind too. Yeah, I'm just gonna watch this for a second here. Yeah, so we rotate through these. So that's just the green light there. Then rotate. And it hits there. That's at 0 volts. Okay, yeah, so no, this isn't. Okay, so it hits the yellow there. Oh, and then this hits yellow here too. I think I see. Okay, let me watch again. I could make one of these myself, actually, is what I should do on the breadboard. I think I'm gonna do that. I'll make that as a as a separate video. I'll put out, I have a counter. Ring counter is what they use. Yeah, I think I'm gonna do this as a video. I'm gonna call the stream here now. But yeah, I think this is a video you might be seeing from me later. Is one where I will actually design a logic circuit that does this traffic light scenario, just because I do find this interesting. And that, of course, like as you can see, I'm not used to analyzing digital circuits still. I'm going through that book too fast. But yeah. And well, thank you for everybody for attending, and thank you, Rohit, for commenting so much here and asking questions. I hope that you enjoy your studies. Here, I'll go. Can I? Oh, yeah. I hope you enjoy your studies in electrical mechanical engineering, and I hope that you come back. And I hope you get some things out of my videos, and I hope you all get some things out of my videos. Yes, good night.